已解锁，请启出话筒。
Testing. Hey, good morning to everyone. Hope you have started your assignment. If you met any problem in your assignment, right, you can try and get hint from me. Okay. If you're really stuck, you can get hint. So maybe some of you are not here yet. Let's start with some highlights from differential equation before we go to new chapters. There's something that I want to highlight from last chapter that we learned. Okay, so what's the differential equation? Yeah, so it's an equation looks something like this: ax plus by equals c. Right. So we want to ask, given ABC, when do you have integral solution? So meaning x and y has to be in Z, such that this equation. Very simple example is like 2 times 3 plus 4 times 2 equals to, let's say, 14. So you want to figure out the 3 and 2. And we show that, I mean, by examples, there might not be just one way, right? There are multiple ways to solve it. Can you give another possibility? Using 2 and 4, the linear combination of 2 and 4 to build 14. Huh? 2 and 3 is just sub 5. Yeah, sure. Do you have other XY? Or... Sorry? 5 and 1. That's right. So 2 times 5 plus 4 times 4. Okay, good. Yeah. But then last time we said that these solutions actually they have relation using the GCD. We have a formula for it. Okay. In fact, I can produce a formula for you to figure out all the other solution. Maybe not all the other, but infinitely many of them. Okay, so here is the point. So let's start with okay, so let's start with this one. Okay, maybe I have to sit here because this audio is magnetic problem. Okay, so when does it have a solution? So if the GCD of AB divides C, okay, then this differential equation here actually has more than one solution and has infinitely many of them. So what are these solutions? So these are x equals to x naught plus b over d n comma y equals to y naught minus a over. So what's d here? So it's a GCD of AB. So stand for all and that where s naught and y naught will solve our original equation. You get one of the solution, you get infinitely many of them. Okay. Not that I use fraction here, but then this fraction is not really a fraction, right? It's an integer because the divisor will divide a and b. Okay, although I write as a ratio or fraction here, it's really an integer because it's divisible by the GCD. And there's some sign here, and some difference here. So maybe you want to do some sanity check to see why this sign makes sense. So maybe you can plug in your solution and see why this sign is really important. Okay, so this sign is really important. You can see that two alternating sign actually cancel out in your calculation. Okay, so check this. And to check this, you really require this. Great. Just to understand. Okay, so it doesn't matter you put a minus here or plus here, but the most important thing is they have to be alternate. They have to be different so that they can cancel out. Can you see that this multiply in and b multiply in can get the same term? So 1 plus 1 minus b cancel out. Okay, so in that way, this, which is true. Okay, yeah. So it doesn't matter if put minus here or minus here, but one, they have to be different. Because it's true for any set anyway, any integer number. So your integer number definitely will pass through a minus, a negative number. So when you pass through a negative number, then negative become positive. It becomes negative instead. So the point here is the different sign of the two. Okay. Then the other case is what if GCD of AB doesn't divide C? The GCD of AB doesn't divide C, then there's no. Okay, so I put a flag there. It doesn't exist. Then there's doesn't exist integral. So maybe today the third time I told you what is inverted E here exists. And so if I slash it, sorry, that's not that. There doesn't exist integral solution. To x plus ey. Um, yeah, so this is a very fascinating statement here. Because let's say I can use GCD of AB to split A and B, right? So A is a GCD of AB times something. B is also a GCD of AB times something else. Okay, then this equation I can split it out to be GCD of AB times MX plus BN equals to C. Then this whole part here is just like, okay, so maybe like this integer. Okay, M is also integer, N is also integer. So you multiply integer again, integer, add integer again. This is what we call closure. Okay, close under multiplication, close under addition. So if this GCD will divide this, right? Sorry, if this can be split up to GCD of some Z, this means what? Actually, C is divisible by GCD of M. Okay, does it make sense? Okay, so if you have this integral solution, actually you imply that this GCD of AB have to divide C. Okay, so it has to divide C that you like. Okay. Maybe you can ask another question, right? Why can't I just replace GCD of AB with some other divisor of A and B? Okay? Some divisor of AB. Do you get what I mean? So maybe let me give you an example. Um, so let's say 6x plus maybe 12y equals to, let's say, 2. So I also can just pull out 2 times, let's say, 2 times 3x plus 4y. Okay, then you can ask whether this got integral solution or not. Yeah, let me see. Sorry, this is 6. Okay, so maybe I just pull out one divisor is enough. Okay, turns out that you need to check for all the divisor. Okay, because GCD will include all the divisor, which is the power pi to the minimum power of the prime that occurs in A. Still remember or not the formula for GCD? So uh, maybe let me write down here. So if A equals to P1, A1, P2, A2, to Pn, An, and then B equals to P1, A1, sorry, P1, B1, C2, B2, out to Pn, Bn. Then the GCD of AB is just Pi, sorry, P1 mean of A1, B1, P2 mean of A2, B2, up to Pn of mean of An. Okay. So you are kind of like picking all the common divisors. Okay, so meaning if you can make sure that your GCD AB divides C, right, you are making sure that all the divisor will divide C as well. Does that make sense? Okay, because if this PI things copy, copy, copy. So if all this PI things divide C, right, obviously all the previous PI, AI, thing, I shouldn't say this. So PI will also divide. Pi Ji such that Ji is less than or equals to the mean of A, more generally. Okay, so maybe I give you some examples here. So let's say to times 2 times 3 times 3 divide 72. Obviously, 2 will divide 72. 2 times 2 also divide 72. 3 times 2 as well. Yeah, all the other possibility as well. Yeah. Or I should replace here and other common devices. Okay, so GCD is like taking care. Okay, taking care of all. Okay. Maybe in class I will talk a little bit more than what you need to know. But then maybe some of you are worried about your exam. But exam will be just about like tutorial or assignment question. If you can do it, then should be good. Okay. Uh, so I'll talk a little more so that you know what you are doing. Okay. So I think a very important thing you come to university is to learn what you are actually doing, because this is not high school. High school is a little bit different, but I think the world education is transforming. Okay, but why high school teaching is a bit like a military style, right? Not military style. I ask you practice this, practice this, practice this. You're not sure what you are practicing because high school is like a mandatory education. So all of you have to go. Otherwise, maybe your parents will be called by police. Yeah. And because everyone have to go, right? Though that means the level is different. Okay, the level could be different. I cannot say this children is stupid or what or good or bad, because I think everyone have different talent. So I think this is a responsibility for the government or the authorities to better provide solution with. But for now, because all sort of different people get grouped inside the same basket, so they have to accommodate the needs of some of the students. Okay, so that's why uh, they try to uniform the solution, uniform the teacher to suit most people. But since you come to university already, so please make sure that what you learn, what you choose is based on what you like. Okay? Because only then you can learn better. Okay? Otherwise, you'll just keep lamenting. But anyway, some of the students like to lament. That is their attitude. But then still, I hope that you will choose what you like. Okay. Any questions so far about this GC? Okay, so maybe today I want to bring you up an idea is that this GCD of two numbers, right, is like taking care of other common devices. Okay, taking care of other. Because if you have a solution like this, right, okay, so you can pull your common devices out. Then that's mean that that common device will divide C. And so if you can make your GCD AB divide C, meaning all the common devices will also divide C. So you settle everything. Okay. So you see, so this is again about divisibility actually. Okay, so about divisibility actually. And to solve the integral solution. Okay, so because divisibility deal with integral without remainder. This is the remainder R is 0. Okay. So far, so good. Question? Any question? Okay, if no question, we will go to the next chapter called Congruence. Well, I think you see congruence before. Do you look at clock every time, your time? So every day, right, you finish 24 hours, it restart. So this is like mod 24. But sometimes people just use mod 12. So you have 24 hours, how to mod 12? How to differentiate 12 in the morning and 12 in the afternoon? AM, PM. So you introduce another name, okay, to differentiate these two. Otherwise, you will use 24 hours. Okay, so one of them is 12 hour, the other is 24. Or 1 a.m. is 10100, and then 1 p.m. is 2323 or 1300. Okay. Right. So we saw what's congruence here. So again, because we learned divisibilities, right? Okay, so we will define congruent using divisibility here. So we say that two numbers are congruent modulo m if a and b have the same remainder when they're divided by m. So in other words, a minus b is divisible by b. Sorry, m. Why? Because they have the same remainder. Okay. So so let's say a. So for example, a equals to PM plus R, and B equals to QM plus R. They have the same remainder. Then A minus B will remove the remainder R. Okay, so that you're left with P minus M minus QM, which is just P minus Q times M, so that it is divisible by M. Okay? Does it make sense? So for example, Y, so let's put our example back to the clock. So Y 0, 1, 0 is the same as, wait, let me think. Are they the same? No, they shouldn't be the same. Okay. Okay, so one way is to write that M will divide their difference, or the other way is A and B differ by a multiple of M. Okay, yeah. Maybe the most useful one is the second one for now. So when we say that A mod A congruence to B mod M, then M will divide their difference. Okay, so this is the most common. Otherwise, you need to remember that. What do you want to remember? Remember that they have the same remainder after divisible by. Can we do some examples? Yeah, so let's do some examples. Okay, so for example, 7 is congruence to 1 mod 3. Okay. So here are the congruence we write double, no, not double, triple line. Okay. So when we write equal, right, it's really equal. We say on the nose. Okay, they are the same number, but these two are not the same number. But after modding out by 3, they are the same. So why are they the same? So well, there are a few ways to check it. So first way is to use the definition, because 7 equals to 2 times 3 plus 1. Okay? And then 1 is equals to 0 times 3 plus 1. So 1 and 7 have the same remainder 1. Another way to check is like what I told you, right? You check whether 3 divide their difference or not. Okay, their difference is 6, so 3 divides 6. Make sense? Okay, maybe I give you a question. You can answer me directly. So whether 2 is 6 mod 2 or not? Yes or no? Yes. Why? Sorry. Maybe you can speak louder. Yeah, can speak louder. 6 minus 2 equals to 4. Okay, and then 2 divide 4. Okay. Actually, there's an easier, we call representative. Easier representative. You know, what is it? Congruence 2 as well. Both of these values, right? 0. Okay, so 0 also congruence to 2 mod. Because 2 and 6 has remainder 0. And so there's the idea here is everything we can reduce them to the remainder. Where we can congruence to some remainder. But then this remainder is really restrictive, right? Because let's say if you divide by 3, right? What are the remainder you get? If any number divide by 3, what kind of remainder you get? 0, 1, 2. How about 3? Can you get 3? No. Why? Because you can push it to the quotient. Okay, you can push it to the quotient. So really, there are only 3, we call it equivalent class. Okay, equivalent classes. Okay, all of them will be equivalent to either 0, 1 for the mod 2 case, or for the mod 3 case, you have 0, 1, 2. Okay, all of them will be equivalent to one of these 3. Okay, one of the remainder you yeah, okay, good. So there's another example here. Maybe get one more. Let's see whether 3 is equivalent to 4 mod 5 on. Okay, is this true? Huh? No? No? Okay, why? What do you mean 2 and 1? 3, 3 mod 5 is wait,
Oh, 3.
what? So what's your reason?
0.
Your reason should be about divisibility, right? Yeah. So what do you need to check? Sorry? 5 doesn't divide 4 minus 3, yeah. Okay, which is 1. Another way to see is everything divided by 5, what kind of remainder you get? 0, 1, 2, 3, 4. Okay, so 3 and 4 belong to different remainder. Okay. Or sometimes same class.
Yes, no.
Huh? Yeah. Okay, either you check this, either you check what's their remainder. So this is one way, right? Second way is right 3 equals to 0 times 5 plus 3, and then 4 is equals to 0 times 5 plus 4. So 3 and 4 have different remainder after dividing by 5. Okay? Yeah. Make sense? Okay, any question? Okay, so now it's a game about remainder. Okay, previously was about GCD, and now it's about remainder. All of them is about divisibility. Okay. So now we care about number that have same remainder. Previously, we care about number that can be divided. Okay. So now we care about remainder. Okay, so next is the set of integers is divided into m different sets called the congruence class modulo m. Okay, each containing integers that are mutually congruent modulo m. So this is like what I told you just now. Why m set here? Because for each congruence plus modulo m, you have m remainder. Okay, 0 up to n minus 1. No, no. For 3, you have 0, 1, 2. 2 and 3, what's the difference? N minus 1, 3 minus 1. Okay, so for example, there are 4 congruence classes modulo 4 here. Okay, so you have all the terms that have remainder 0. So these are the multiple of 4. And then all the terms that have remainder 1 after dividing by 4. So can you observe anything? How do you get this line here? You just plus 1 to the class of 0 here. Then you get this. And then how about class 2? You just plus 2. 0 plus here. And then 3. What if you plus 4 again? You can see that you get back to the same 0 class here. Just that it gets shifted. If you plus 4, you go back to the same set of numbers. Okay, so sometimes we will write like this. There's one notation, very useful notation here is we'll write that 0 bar. Okay, 0 bar equals to 0 4 4 8. I'm not sure, maybe some of you in discrete math see this notation before. Otherwise, this is a very handful notation to use. Okay, so we kind of like upgrading. Okay, we kind of upgrade our number to a set of numbers. But this is a very handful thing. Okay, so in this case here, that's why we call it classes. Okay, because it's a set of things. Okay. Really, they are not integer, but they are set of integers. Okay, so we call these classes like 0 bar, 1 bar, 2 bar, and 3 bar. That makes sense? Okay. So we collect all the integers that have the same remainder together. Because they are the same in this world. In this congruence world, they are the same number. We treat them as the same. Later you will see, because in the usual operation, we will see that they behave the same actually. Okay, so they behave the same. In particular, they behave the same as their representative. Okay, we call these representative. Representative can change, right? Like class rep. In this class is you, in the other class is a different person. So sometimes 0 bar here we could write like it's a 4 bar. Okay, we can change the representative. Okay. Because if I write 4 bar here means what? I want to have all the guys that have the same remainder as 4 after dividing them. It's the same as 0 bar. It's the same set. Okay. So representative, you can really pick anyone from the set. Same set. Okay, so far, question? Okay. Next, a complete system of residues modulo m. So this residue here is actually the remainder that we keep talking about. Sometimes we use residues. Residue is like leftover if you do science experiment. Right? So if you mix some chemistry together, there's some residue that's left over. So a complete system of residues modulo m is a set of integers such that every integer is congruent modulo m to exactly one integer in the set. Okay, so for example, just now we talked about mod 4, right? So what's the complete system of residue modulo m? So you want this complete set here of integer such that every integer is congruent to exactly one of them. Yeah, it's exactly one of them. So just now we talked about remainder, right? So if you are mod 4, how many kind of remainder you have? So there are 4 of them. Okay, 0, 1, 2, up to n minus 1. So in this case, here is 3. Okay, so this is a complete system of residue mod 4. Okay, so another example was what's a complete system of residue mod 7? Okay, you could do 0, 1, 2, 3, 4, 5 up to n minus 1. 7 minus 1 is 6. Okay, or you can pick a different one. Okay, you can pick minus 3, minus 2, minus 1, 0, 1, 2, 3. Why? Yeah? This is like what I said just now, right? You can pick different representative. So you can see that these things is like partitioning your integer. Okay, it is like partitioning your integer here. Okay, so it's like 0, 1, 2, 3, 4, 5, 6. Okay, every integer will belong to one of this part of the cake. This infinite cake. But then they give another possibility here, right? Okay. So 0, 1, 2, 3 appears already. But how about minus 3, minus 2, minus 1? Okay, can you see which part of the cake belongs to the minus 3, minus 2, and minus 1 belongs to if I slice it differently? 4, 5, 6. Okay, so minus 3 is staying with which part of cake? Minus 3. 4. Okay, minus 3 is here. Okay, so minus 3 is here. Minus 2, 5. Minus 1, 6. So how do you calculate this very quickly? Okay, so one technique is you can just add multiple of 7. Okay, so minus 1 plus 7 is 6. So minus 1 is congruent to 6, 7. Okay, yeah. Then this will be related to the third part of the definition here. Okay, so you can keep adding multiple of 7. Okay. So if you observe here, what is the relation in the row? They are differ by a multiple of 4. Minus 5 plus 4 becomes minus 1 plus 4 becomes 3 plus 4 becomes 7. Okay. So within the same group, they are differ by multiple. Okay, very good. So maybe I give you 2 minutes, work out this. Okay, maybe write at least 3 of them. Okay, write 3 different. You can write more than 3. Try write down 3 different complete systems. Okay. Give you 2 minutes. You can try and discuss with your friends. Introduce yourself. Okay, so let me start with the easiest one. So the easiest one is 0, 1, 2, 3, 4, 5, 6, 7, 10. Okay. So I will write it like this as a set form because it is a set. So to be precise, here I should put set notation before. Okay. Okay, so who else? Do you have other set different from this one? Anyone give one? -1, 0, 1, 2, 3, the same. Keep it the same. Okay, good. For the rest. But then you are not including. And how about other? Shift it. Okay. How you shift it? From -2. Okay. Okay. Next answer cannot be shifting anymore. Maybe more creative one. Anyone? -10 to 0. Okay. -10, 0. So you mean like -10, -9, -8, 6, -4, -3, jumping number, -5, -4, -3, -2, 0. Okay, so maybe it's interesting to figure out what are these. So maybe -1 is 1, reference to 1, then -9 is reference to 2, 3, 4, 5, 6. Okay, so you are kind of like reversing the order. Any more creative one? Any more creative one? Or any other that different from these? I'll try. Purple color. Who are you? What's your name? Yeah. What's your name? Wang. 诗涵，有翘舌。诗涵 you 诗涵 okay. Do you have a different, can you give a different tick system? Hmm. No, infinitely meaningful. Okay, 0. 12. Wow, good. Very good. Then 24. 24. Okay, good. 36. Okay. I think I saw your pattern. Okay, good. Okay. Okay. And then 96. 96. Next. Uh, Now you can calculate at your phone. I mean like on your iPad. Yeah. But I think I sort of see your pattern. You try to get like n times 11 plus n. Okay, good. So basically this is 1 times 11 plus 1, and this is 2 times 11 plus 2, And then let's check. 3, 4, 5, 6, 66. 66 plus 6, 72. 77 plus 7. You missed out one. 77 plus 7 is 84. And then 88 plus 8 is 96. 99 plus 9 is 108. Then 110 plus 10 is 121. Good. Okay. Yeah. So you just add a random. Don't need to be that regular actually. You can even jump further. So you can take like 0, 12, -9, and then blah blah blah. Doesn't matter. Yeah. As long as you pick at least one, okay, from the is congruent. Yes. 1 to 0. Okay, yeah, thank you. Yeah, so this is 111 plus. Wait, no, right? Oh, 110. Wait, so let me see. Yeah, 110. Because it's 10 times that. Okay, good. Very good. Yeah, so as long as you pick number enough so that your integer can sit exactly one slice of this. Okay, so sometimes we call this a partition. So these this equivalent class or this system will partition your integer. Okay. Notice that one number cannot sit at more than one slice of the cake. You cannot have two different remainder after you get divided. And you can only sit at one, exactly one. Okay. Either you are divisible, either you are not. If you are not, you have a certain remainder. Okay, let's go to the next one. Let's go to this theorem here. So if A is congruent to B mod M, so if they have the same remainder, then if I add a number, same number to both of these, they will also have the same remainder. Or if I take away the same number, they will also have the same. Or if I multiply by the same number, they also have the same remainder. So if you remove this mod M, right, this is what it is true in number system. For now, what we want to tell you is it is still true after we introduce this new number system. Okay. Modular M number system. Does it make sense? Okay, so or in other words, if I don't write this mod M, right, I can write like A bar plus C bar is B bar plus C. Yeah, we can add it as a set like that. Okay, should I prove it to you? Okay, I'll prefer prove it first. Please bear with me here. Okay, so this proof is really simple. Just need to know one definition is enough. So A modulo B mod M, if and only if M divide A minus B, divide their difference. Okay, so we're just going to use this to see why these things are true. So since M divide A minus B, this is given by the assumption. Okay, so what you can see is M will automatically divide A minus C, sorry, A plus C minus A plus, B plus C, because plus C minus C, you get back to 0. Okay, very cool. Cool. Okay. Similarly, you can immediately see the part B. Right or not? Okay, the same game we will play here. M will divide A minus C minus B minus C. Again, you see a plus C minus C thing popping up here. Okay, how about the last one? Is the last one tricky or not? So the question you want to ask is, does M divide AC minus BC? But what is AC minus BC? C times A minus B. But M will divide A minus B. Obviously, it will divide C times A. Okay. Okay, in that case, maybe we can quickly go through one example before we having a break. So let's see an example. So we can see that as 19 modulo 3 mod 8. Okay. What can we do here? We can see that actually 19 plus, let's say 7 is the same modulo with 3 plus 7. Is it true? Okay, is it true? So we need to compute what are these two numbers here. So one of them is 10, the other is 26. So I write equal here because I'm really calculating the addition. Okay, but we want to decide whether 26 and 10 are congruence modulo 8 or not. Obviously, 26 is not equal to 10. Okay, so that's why we need this second symbol here. Okay, triple equal. Okay, they are not the same, but we claim that they are the same after dividing by 8. I mean, their remainder are the same. Okay, is their remainder the same? Same. Okay, so you need to write division algorithm. 26 equals to 3 times 8 plus 2. 10 equals to 1 times 8 plus. Okay, so they have the same root. Make sense? Okay. Yeah. So you can think of this new system here, right? Work exactly the same as the usual number system. Okay. You add the same number to both sides. You preserve the congruence. You preserve the congruence. If you minus a number from both sides, you preserve the congruence, and then if you multiply with the numbers, you preserve the. Okay. Any question? Okay, if no question, how about we take a 10-minute break and then we'll come back at 10:02.
将话筒放回，请将话筒放回。已上锁。
本来就大家肯定这里面只有两个很危险的一个信息单。
Hey, hi. Hi. Okay. Yes.
然后加一个以后嘛，
这个是这个说每一个 integers congruent M 都必须
开着都就
OK，所以每一个 integer 都会 congruent module to M2 其中一个号码。所以是说什么叫做 integer congruent M？就是说它会和就是不是其中一个，只有那一个，就一个 exactly one 里面的其中一个，OK， 只有那一个 他们有相同的 remain 的。OK，比如说你选另外一个数字嘛，可能11，哪一个是congruent？对，对起来的时候说11除7的 remainder 是4，说他说这个是一样，和4是一样。呀，然后它要 complete，就是说，每一个 integer 都会属于其中一个。如果你想想看啊，我把这个6丢掉，then 6和谁是相同的？congruent 没有，因为6跟6这几个相同。Sorry，复数是什么？复数可以啊，复数也可以啊，negative integer 可以啊，没有问题啊。你选一个啊，比如说减11嘛，减11的 remainder 是多少？不是负数嘛，你的负可以放在quotient那里，因为负11，刚才说负几啊？负11 OK，负11等于减1乘7，sorry，对，负11等于我想一下，2乘7，sorry，有的，-2 billion，对，没有错，对，你能够一直确保你的 remainder 是活在0到 n 减，对，嗯哼，
余数一定是正数，
对，没有错，余数一定是正，
这个也不一定连续的。就假如说
不一定，
我把这个3换成4，不也一样成？
没有错，没有错，对，刚才我们不是有一个例子是跳跃，来给我试这样，刚才我们有一个例子是可以跳，只要确保它是 complete 的，就是每一个
请提出话筒。
对标是这个了，这是最。
读者，请起出话筒。
Okay, for those who are here, I'll take attendance first. 周书月，施杰生，施杰生，方家豪，厉承炫，周红婷，朱祥 Rainbow is Rainbow here no? Not here. 陈意涵，韩希莹，刘真贤，姜通俊，叶伟通，OK，陈子涵，王金珍，王金珍， 竞争，王竞争 ，OK，空一架，陈子，胡崇瑞，陈诗曼，何嘉诚，何嘉诚，I think I saw 嘉诚，OK，冰珍，you not back yet，林浩云，浩然，心仪，陈心仪，天文气，天文气，OK，张小柔，张小柔，OK，张泽瑞，陈凯莹，陈凯莹，no no yet。Tiffany, yes. Check it. Yasin and Jasmine in their toilet. Jiajing, Jiajing, okay, Jiajing. Liang Jiayue, Lu Zexing, Wei Mingtao, Yang Xucheng, Zheng Yifei, Chen Yuqing, Chen Yuqing, okay. Li Lingyi, still here. Cao Huayang, Cao Huayuan, sorry. Cao Huayuan. Wang Ya. You managed to get your Buddha? Okay. Li Haochong, Liu Yishu, Pan Ziliang, yeah. Gan Jinghao. Oh, you just came. Ho Mingshen, Li Weihan, Ayub, Saudi Ayub, Saudi Ayub. Joy Lee, okay. He Minghao. Let's continue first. We will pay attention again later. Okay, so just now your friend come and ask a question, right? So I put most of these. Oh, it's okay. So first of this one is like kind of a standard one. So this is the standard one. Maybe you ask a question, let's say -1. Where does this -1 belongs to? If you're gonna write it as a portion of 11 plus some remainder. So the point here is this remainder, right? You can always keep it in between 0 up to 11. Okay, so or more generally is n-1. Okay. So how do we do that in this case? Maybe I don't take -11, maybe take -14 for this purpose here. So in this case here, we can push it a bit further, right? So let's say -14 could be written as 2 times 11. Sorry, no, this is not the way to do it. Let's say 1 minus 1 times 11 plus 1. Wait, which one is better? Okay, I think we have to do a bit more. So, okay, so I think when you do this, it's better that you have a number line in your mind. So let's say 11 minus 14 is here, 0 here, 11 here. Okay. So how can you push your remainder into the range of 0 to 11? Okay, so then you want to keep your R positive, right? Okay, so then it's better to make this part to be more negative, a bit more. Okay, so how much more? Just a little bit. Okay, so is -22 enough? Okay, so meaning, let's say if I take -22, how far am I away from the -40? It's just plus 8. Correct? Okay, so you can make you can always make your remainder in between 0 and 11. Okay, if you make it too far, then it doesn't fulfill its purpose. So, okay, so let's say if I make it too far, so what do I mean by too far? Let's say I go to negative 33. Then how do I go back to negative 14? How much more I need to add? Huh? 19? 19? Yeah. Then 19 doesn't fall between the range of 0 and doesn't fall between the range of 0 and 11. Okay, then it doesn't fulfill the purpose. So the point here is you can always find a number such that it is this close, 0 to 11, close to negative 14. Or in other words, is how to find a number around. So maybe around here is the range of this. Yeah. Yeah. Okay. So okay. I think another convenience way to think about this is you can split your number line into multiple of 11. So let me draw it for you. So here you got 11, here you got minus 11, and then here you got minus 22, right? Then minus 33, and then on the other side you have 22. So you are within 11 distance and the length of 11 distance just through your minus. And you cannot pick too far away. Okay, so this is the range. This range is 8. Okay, for the rest, it will be too far away. Okay, does it make sense? Have you think of number like this before? Measuring distance? No. So this is the geometry of your numbers and how far they are at distance. Okay. Okay. Okay, let's continue. Okay, let's continue. Is how about we add different number both sides? Okay, the congruence will still hold as long as your C and D are the same mod n. This is slightly different from your number system. This is slightly from your number system because in number system, right? If 2 equals to let's say 2, right? Okay, you must add like the same number to both sides so that they are the same. Okay, there's nothing like 2 plus 4 equals to 2 plus something else. Okay, but in this number system, as long as the two things you add are the same up to modulo m, okay, they will be the same in the modulo m. Okay, more flexible. Okay, more flexible. Okay, the proof is similar to what we had before. Okay, maybe let's do some examples. Let's do some examples to see this. So let's say 2 is equals to 13 or 11. Okay, are they the same? 13 minus 2 is 11. 11 is divisible by 11. Okay, good. How about pick another one? 5 is congruence to. Do you want to pick one? 16. Okay, good. 16. And very straightforward. 11. Then we will say that 2 plus 16 will be congruence to, let's say, 5. Sorry. So 5. Yeah. So will be congruence to 13 plus 5. Is this right? So A, B, C, D. Okay. Okay, maybe I swap the CD. So CD here. Okay, then this is A, this is C, this is B, this is D. Good. Okay. So let's check out. So 16 plus 2 is 18. 13 plus 5 is 18. Oh, this is not a good example. Too easy. 18 minus 18 is 0. Okay, let's get another example. You want to play with the same mod? 11, negative 6, modulo 2, 5, mod 11, okay. And then you can do what you want to do here. Okay, sure. So 2 plus minus 6, modulo 13 plus 5. So one side we still get 18, the other side we get minus 4. So we claim that these two are the same. So why are they the same? Because 18 minus their difference, okay, which is 22, is divisible by 11. Okay, or you can see that 18 is equals to minus 4 plus how many multiples of 11? Okay. Okay. Any question? So in reality, this is just for sanity check, but then you can straight away use as long as you have this condition. Okay, as long as you have this condition here, you can apply this. Okay, so meaning you can multiply on both sides, or you can subtract or addition from both sides. Maybe you might ask a question. There's one more operation I forgot. Can I divide? Can I get something like this? A over C equal B over D. Can I do this on? Okay, the point here is you don't know what is divisibility here yet. Later on, we will introduce it by introduce a concept called inverse. Okay. Yeah. So far, we don't know what is divisibility in this word. Okay, I don't know how to divide. I mean, you need to find a proper way to define it. Okay, such that it makes sense. Okay, so let's continue. So the point here is it is a bit more than your number system. Okay, more flexible than your number system. All right, so next example. Try and find the remainder when 10 factorial is divisible, divided by 11. Okay. I guess this number doesn't appear in your calculator. Can you try and click 10 factorial and your calculator get it? I suspect no. Maybe it's too big. Is it too big? Or is it still workable? Still work. Okay. So if you're going to divide by 11, can you find the remainder? Okay, maybe your calculator give you a bunch of this decimal, but then you can try to convert it. But then we should use what we have learned just now. Okay, we should use what we have just learned. Okay. So basically, what we should do is we try and dissect this number here. What is 10 factorial? 10 factorial is 10 times 11 times, sorry, yeah, 9, sorry, should go down, not go up. Okay, so 7. Hey, does everyone know factorial? Should I define it? Everyone know factorial? Everyone good with this exclamation mark? Okay, so n factorial. I think for this class of purpose, you just learn that this is net n times n minus 1, n minus 2, all the way up to 1. Okay. Okay, because these numbers are kind of like big. Okay, if you better, right? But then we just want to know about remainder. Okay, we just want to know about remainder. But then the congruence will give this convenient way. You still remember? If you stay in the same congruence class, they will have the same remainder. So you just try and make these numbers smaller. Then make it smaller so that you can compute it. Because we just want to know remainder anyways, right? I don't want to see the division algorithm, everything. So we just want to know about remainder. Okay, so the main thing is the keyword here is remainder. Okay, so congruence deals with remainder. If you know that this number is congruent to some number, okay, that you know how to compute the remainder, this is good enough already. Okay, you don't need to compute the exact division. Okay, so what do we do? Okay, so we know that these 10, 9, 8, 7, right? They are congruent to some other numbers in the world of mod 11. Is it true? Okay, so for example, yeah, for example, 10 is congruent to -1. Okay, 9 is congruent to -2. 8 is congruent to -3, and then -4, and then -5, like that. Okay? And then we can keep the other number the same. Okay, so why this congruence works? This is exactly by the previous theorem. Okay, if we know each term of it, they are the same congruence. Okay, then we will know that the new product is congruent to the old product. Okay, so for this part C, okay, as long as we can know the individual terms are congruent mod M to each other, then the new product will be congruent mod M to each other. Okay, so you can replace with the new terms. Okay, so I guess this is slightly easier to compute, right? Okay, so they are paired up. In other words, you are considering the square of these 1, 2, 3, 4, 5. So what are the square of them? Maybe you will get yeah, cool, very good. But then yeah, sure. Okay, let's do that first. So -1, -4, -9, and then -16, and then minus. Yep. Sorry? Then what do you want to do? Three times 2, 6. Okay. 6 times 4. 3 times 4 is 12. Oh, okay, yeah, cool. That's another way to combine them. Because 12 will be 1 more. Okay. Sure. From here, you can see that there are like 5 minus 1 here, right? Okay, so you can cancel out 2 by 2, just left with -1. Okay. And then you can further do the same thing, right? Okay, because 1635 is kind of big. So maybe you get -1. And then 4 maybe is more enough to keep. 9 maybe you can make it to -2. And then 16 make it to 5. 25 make it to 3. Okay. Yeah, good. So you can do like this. Sorry. So 1 times 2 times 4 times 5, 3. Okay. Okay. Extra 4. Okay. So like what Isaac said, right? Or maybe you make it 12 plus 4 times 3. Why 12 is nice? Because it's just 1 more than 11. So it becomes 1 again. And then you get and 1 more. Okay. So it's very important you keep this triple sign here. When you have this triple sign, make sure you write Now mod what? Because if mod 7, mod 2 is a different story again. So this mod of this number is very important. Then we need to verify this 3%. Okay. Obviously, you see this line, this number, right? This number is like 24 times 5 is like 120. So 120 obviously is different from 10, but they have the same remainder. Okay. So now you see that this big number here will reduce to 10 mod 11. But 10 mod 11, you know what's the remainder, right? What's the remainder? 10 mod 11. 10, just 10. And so in this case here, since 10 factorial is modulo 10 mod 11, and 10 as remainder 10 divided by 11, 10 factorial as the remainder 10 as well. Divided. Okay. Yeah. Any question? Okay, so you can use this mod operation to help you to find remainder. Okay, instead of doing the division algorithm, you divide all the way until you find remainder. Any questions so far? Okay, if no question, how about try this one? 10 to the 10. Okay, I give you 3 minutes. Try to find what's the remainder. So this question is divided by 7. So it's a mod 7.
Okay. So what do you do here? So I think basically what you need to know is you need to know what is 10 to the 10. Okay, basically it's like multiplying 10 times. Okay, so yeah, 10 times of 10. So by the congruence law, right? Okay, so as long as you can found this congruent to some other number that you know how you find the remainder, then you will know the remainder of this large, huge number here. So we kind of split it into products, right? So again, this theorem become very convenient, okay? Because you can replace every term inside your product to a new congruence here. Okay, so in this case here, we're gonna replace 10. So because we know that 10 is congruent to 7, sorry, 3 mod 7. Okay, so we can replace the 3 here replace the 10 here to be 3. So 10 to the 10 congruent to 3 to the 10. So remember to write mod 7 whenever you see this triple sign here. So what's the next simplification you could do? What's the thing you do next? What can you do next? Huh? Right? Make it 9. Okay, so maybe you combine 2 by 2, right? So you combine 2 by 2 becomes 9 to the 5 mod 7. So you have 5 times 9. Okay, so then you just make it 2 to the 5 again. And then what do you do next? So there are like 5 of them, right? Huh? Yeah. So what can you do? Yeah, try. It's 8 times 4. Okay, so you group them by 3, group of 3 and group of 2. So 8 times 4. 8 is a good number here. Okay, so because it's just 1 mod 7. So why I say it is good because it's related to 1. 1 is very good in a number system because everything times 1 is everything. So, okay, so 4 mod 7. Okay, you are done. Because 4 is less than 7. A number between 0 and 7. So in this case here, what's the remainder? So the remainder when 10 to the 10 is divided by 7 is what? 4. Good. Because 4 divided by 7, the remainder is 4. Okay, is it convenient enough? Okay, so then you will see that you have a large number. If you can find the prime factorization, then you can use this method to simplify it.
But you can always find a prime factorization. Do you know? By fundamental theorem of arithmetic. You can always find a prime factorization. But I guess the problem here is what if you can't find a prime factorization? Meaning what? It's a prime number. Then that one you have to do original method. No choice. Okay. Okay, you cannot use this convenient way to do it. Does it make sense? Make sense? Okay. Let's see. Okay. I guess next question. Next question. Okay. Maybe discuss about this. What's the last digit of 12 to the 2023? I guess this lecture notes is built on 2023. So that's why they write 2023 here. I also computed for 2026, if you like. But then the problem here is they want to figure out the last digit. Maybe you go into a calculator and press it. Can you press it again? Can you find this? Cannot. I don't think Google can either. You can try Google. See, Google can compute this one. Too large, this number. Okay, too large. Okay. But then what does it mean by last digit? What could the possible digit you can see in your number? 0 up to 9. So meaning what? This is mod what? Mod 10. Good. Okay, so you just solve this by mod 10. Okay. Yeah. So our number system is called decimal expansion, right? So decimal. So it's mod 10. Okay, in our number system. Yeah. So I'll leave it for you to compute this. Okay, it's the same thing. Yeah, I'll leave it for you to do. Let's skip this one. The solution is 4, I guess. Okay. If we consider 2026, I think the solution is 2. You can go back and exercise. Do practice. So I'll just give you an exercise. Also exercise 12 to the 226. I think this one is 4 mod 10, and the other one is 2 mod 10. Okay, let's continue. Right. Okay, so next theorem is a very interesting theorem. This is sometimes what we call the, can we call it? Maybe I call it. Let's call it, I'm tempted for this thing. Can I call this? Okay, let's not do it. Okay, no name. So if A, B, C, and M are integers such that M is greater than 0, okay, so always we'll put a positive integer, mod a positive integer. And then if D is a GCD of C and M, then AC congruence to BC mod M implies that A and B is congruence mod M over D. Okay. M over D. Okay, so meaning if you consider mod M over N, you can cancel out the C. You can cancel out the C. Okay, you can remove the C. Yeah. Maybe I won't present this proof, but I'll give you an example. Okay, so there's an examples inside your note. So let's say 6 is congruent to 18 mod 12. Okay. So what you can see here is this is 2 times 3. congruence to 2 times 9. Okay, that one not good. So because we want the same C, right? So meaning I need to push up my 3. So I got a 6 here. Yep. And then what's the GCD? What's the GCD between C and M here? So maybe 3 and 12 here. You can use Euclidean algorithm, but then I think this is an easy, straightforward example. You can see that this GCD is 3. So in this case here, the theorem tells you that 2 is congruent to 6 mod 12 divided by 3, which is mod 4. Okay, good. Yeah. Is it okay? Does it make sense? Okay. How is this useful? Yeah, this is not useful yet, but the next part is useful. So far, okay, no? Okay. This one is not very nice yet, but the nice part is this one. This is a cool part. This is what we call a cancellation law. Okay, so let's say the GCD is 1, then this mod M here will remain unchanged. Okay, previously it's M over D, right? But here is M over 1, it's just M. So this tells you that when can you cancel C from both sides? Okay, it's exactly when the GCD of this number that you want to cancel with the mod M, the GCD is 1. Okay, only then you can do this cancellation. This should remind you on the number system, right? For example, let me think. Let's say, wait, what's the cancellation you do in high school? Okay, so maybe do something like this. 2 times 4 minus 2 equals to 2 times 2 plus 2, like that. Okay. So your high school teacher, did you tell you that you can cancel 2 on both sides? How are you get taught in this setting? How do you get taught? If got 2, cancel both sides. Is it? How you get taught? I think here got a different nationality, right? Got China, Malaysia, got Indonesia, got Indonesian. Any Indonesian here? Indonesian. Okay. So did you learn this? Can cancel 2 from both sides? What your maths teacher tells you? Just cancel. Nothing else. Sorry? Okay, good. This is the right reason. Okay, you have to multiply half on both sides. Okay, you actually multiplying half on both sides. Does it make sense? You multiply by the same number. Okay. But in this case here, you straight away cancel. Magic. This is magic. Okay. You straight away cancel. I haven't tell you divisibility here yet, right? No divisible here. Okay, so we call it a cancellation. So you can cancel the C on both sides. Okay. So the key here is this GCD. This GCD is very important. Later we'll come back to this thing again. And then you will see better how this thing works. Okay, so you need to make sure that your GCD of the thing that you want to cancel with the mod M is 1, only then you can cancel for now. If you want to think about that reasoning, right? So meaning when GCD of C and M is 1, only then you can find something called 1 over C. Okay, later we'll come back to this idea again. But then let's learn this cancellation. Okay. All right. For example, this example here. Is this example good? Yeah, this example is good. Okay, so 100 is congruent to 1000 mod 9. We say that it is implying 1 is congruent to 10 mod 9. Why is it true? It seems like the C is 100 here, right? Okay, so the question here is 100 GCD of 100 and 9 equals to 1. Is it true? Okay, well, one way to see this, one quick way to see this is you can split 9 to 3 times 3, 100 to 2 squared times 5 squared. Yeah. So their common divisor is 1. Yes. So by previous theorem or by cancellation law, call it 1 times 100 congruence to 10 times 100 would imply 1 congruence to 10. You remove the C. Okay, so far so good. So far so good. Any question? Okay, yeah. So the GCD of C and M equals to 1 is really important before you do cancellation. So in general, you cannot simply do it. So let's say, for example, let me think. So let's say we pick some easy one. Let's say I do this. 2. Yeah. Okay. Agreed. 2 is congruent to 3 times 2 mod 2. I just pick 2 representative from the class of 0. Okay. So can I infer that 1 congruent to this one not good example. Should I change something else? Let's change something else. Let's see. Let's work out some bad examples. So say you maybe put a 2 here. Or 6. 3. Yeah, I think this is okay. Yeah. So 2 is congruent to 6 mod 4. All right. Okay. So can I just do cancellation law by cancellation law? Okay, by cancellation law. 1 is congruent 3 mod 4. And so what's wrong with it? What's wrong with it? The GCD of 2 and 4 is 2, not 1. Okay, so this GCD condition is very important. Okay. Yeah, so you cannot use the cancellation. In other words, when I give this examples, it means that when you read cancellation law, right, you cannot just read this. Okay, there is some condition coming in. You need to read the whole thing. Okay, from the start to the end. You cannot just read end. A lot of people, when they read stuff, they just read conclusion. Wait, tell me the conclusion. Tell me the conclusion. Conclusion is important. I didn't say it's not important, but then you need to see how this conclusion comes. Okay. Okay, so there are some conditions that you need to check. Okay, the GCD problem. Okay, so that's why you learn GCD first before congruence, because we need GCD. Okay, to work. Okay, let's continue. So next theorem is if you have 2 congruents, then these 2 numbers is the same mod, they are LCM. Okay, if you still remember, this notation is for LCM. F1. So what example I can give you? Maybe not proving to you. So example is this. So let's say 37 is congruent to 85 mod 6. 37 is congruent to 85 mod 16. Then we also know that 75 is congruent to 85 mod 48. Okay, so do you still remember how to figure out this 48 here? There's some convenient way, right? So if you write 6 to be 2 times 3, and then 16 to be 2 to the power 4. Okay, so what do you do here? This is just P1 to the max of A1, B1 times P2 to the max of A2, B2, right? So there are only two PI you need to take care. So one of them is 2 to the max of 1 and 4. The other one is the max of 1 and 0. Okay, so it's 2 to the 4 times 3, which is 48. Okay. Otherwise, you can list down their multiples. There will be the traditional method. 6, 12, 18, 24, and then list all the way up to 48. And then similarly here, 16, 32, and then 48. Okay, so is it true? Can you verify this is true or not? 37 is mod 85. Is congruence to 85 mod 48. Okay, so you write, you check up. So check what is 85 times how many? I think 1 is enough, right? 1 times 48 plus 37. So they have the same. Okay, cool. Okay, good. Very good. Next. So construct a table of addition modulo 5 and a table of multiplication. Okay, let me do one and then you will do one. Okay, let me do the easy one. Yeah, let's do the one for addition. So why is this possible? Because we just care about modulo m, right? Okay, everything reduced to modulo m, there's just, what's the complete system here? So there are only five elements. So which is 0, 1, 2, 3, and 4, n minus 1, up to n minus 1. So there are n because you start with 0. Okay, so you write down all the possibility, how they end up there. Okay. So 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2 is 2, then 0 plus 3 is 3, 0 plus 4 is 4. Then 1 plus 0 is 1, 1 plus 1 is 2, plus 2 is 3. Kind of shifting by 1 of first row. So 4 plus 1 is 5. So that means what? It becomes 0. Okay, so this part. I mean, to be precise, I guess we should put a bar on the top. Should be precise. Otherwise, please remember you are working with mod 5, so that's why you only have 5 numbers to work with. Okay, otherwise to differentiate, you should put a bar at the top. Okay, how about next one? So you get 2, 3, 4, 0, 1 like that. And then 3, 4, 5, 6, 1, 2. And then 4, 0, 1, 2, 2. So a bit like a Sudoku. There's no repeating. This is very interesting, and there's no repeating integer across a row or column. There's no repeating. Sometimes we call this a bijection. There's no repeating. Can you realize every column, every row, there's no repeating. This is not a coincidence. This forms something what we call a group. Group in the abstract algebra sense. That is a group. Okay, so now it's your turn. Okay, now it's your turn. So how about instead of addition, we do multiplication. Let's let you work out the table. Okay, so instead of addition, you put a multiplication. Okay, see what the table you get. Try, give you 3 minutes. Yeah, so make sure if you can, you put a bar at this top of this number, or in any way you mention something mod 5, okay, table mod 5, table of addition. If you don't want to add the bar there, because otherwise, why would you just stop at 4? Why not continue? Okay, this is a very big problem here, because actually we are considering infinitely many multiplications here. Do you understand? Because if you are considering 5, actually you are looking at the number 1. And so this table actually include all the here. Okay, so either you put a bar here, either you mention somewhere what kind of modulo you are doing. Okay, anyone work out this? I guess there are two very simple row and column, right? Where you just get 0 all the way. Okay, maybe someone can tell me what's the second row is. Second row. What's the rest? Still easy, this one. Multiply by 1, right? That's why you just get 1, 2, 3, 4. Okay, how about the third row? Want to try anyone? 2, 4, 1, 3. Okay, good. I get the same thing. Third row then? 3, 1, 4, 2. Good. 4, 2. And then? 4, 3, 2, 1. Okay, very good. So can you see from this table here, we don't quite have that property that every row only have one kind of number appear. Now, for example, this row here, this column here, 0, 0, 0, 0, 0, 0. Where 0 is appearing multiple times. And then first row is also the same. And first row is also the same. But then, can you notice that if I throw away the number 0, I still have this non-repeating row and column. See? 1, 2, 3, 4, 2, 4, 1, 3, 2, 3, 1, 4, 2, and 4, 3, 2, 1. Can you see it? Can you see it? If you just throw the 0 away, this 1, 2, 3, 4 actually also form a group multiplication. Also form a group. Yeah. And then the other thing I want you to notice here is this position of 1 is very special. Again, this position of 1 is very special. What you can see is 1 times 1 is 1. Okay, very obvious. But 3 times 2 becomes 1 in this world. Because in the usual world, it's just 6, right? It's a big number. But in this world, I reduced to 1. You still remember what I told you about number 1 here? 1 is the identity. And then 3 times 2 can make you an identity. And then what's the other way to make 1? 3 times 2. Okay, 2 times 3, 3 times 2, because it's commutative. You get the same one. And then the other one is 4 times 4, also get you 1. Something square back to 1. Okay? Yeah, these things are very important. Later we will recall this property. Okay, so far, any questions so far? So far, any question?
So I want you to observe is this table is the number is permuting. It's permuting. Okay. And then how to get the number one.
And we left as an exercise. You can go back and construct modulo 6. You can ask yourself, do you see this permutation observant, property again? Okay. Did you see this permutation property? I can give you some trailer. I can, what do you call it? Spoil you. Okay, spoiler. Give you some spoiler. You go back and verify yourself, but I'll give you some spoiler. The spoiler is addition still form a group. You can see that every column, every row does not repeating numbers. But for multiplication, it doesn't work already. Okay, even if you throw away the zero, it doesn't form a group. You can see that you see this column of 2, 4, 0, 2, 4. 2, 4 is appearing twice. Not really. So 5 and 6, what's the difference? What's the difference? Can you notice what's the difference based on the concept we teach you these 2 days? What's the difference between 5 and 6? Sorry? Good. 5 is prime. 5 is prime. Very good. Then 5 is prime. Okay, very good. 5 is prime. But let me tell you a magic. Do you want to know a magic here? Let's say if I throw away 2 and 4, right? Throw away 0. Did you see non-repeating numbers appearing again? Did you see? What am I throwing here? 2, 0, 2, and 4. What's the relation between 0, 2, and 4 with 6? They are GCD. No. Yeah, their GCD is not 1. So I just keep those that are relatively prime to 6. And then you will form a group. Hey, sorry, should I throw 3? Yeah, I should throw 3. Yeah, throw it. Just throw it. Okay. Okay, throw this one as well. So you form a group again. Very simple group one in this case. Actually, it's a Z mod 2 group. I will say it's an isomorphic, but then, yeah. I'll just keep it in this way. Okay, form a group.
Okay. 2 different elements.
That's true. Why I'm saying it's Z mod 2, because if you form a modulo 2, this is extra thing, extra knowledge. So if you form modulo 2, right, the addition table here, you get 0, 1, 1, 0. Like that. There's only 2 different elements except this one. Sorry, this one is the addition. Okay, so we shall take a break. Here, this is an exercise. You can go back and verify this. Okay, so let's take a break until 11:09. So I'll continue with attendance taking. 黄旗子，黄旗子。青之相，胸胚称，张馨予，张馨予。周瑞明，赖文义，陈子，陈子睿，李小环，OK。曾天健，曾天健。Aaron，孙瑞全，Isaac，西宾科，高硕here，here。王诗涵here 了，here。所以再次说，OK 好，可以。司仪是刚才我教的，哦，司仪是你，哦，你没有来2天，刚回来，OK。明显。算分呢？睡不醒，打太累了。OK。李心宁，OK。嘉凯，林嘉凯，OK。林卓娜here 呢？陈家福，汪冲铺，武艺，崔文倩，参序，OK。宋兰坤呢？小嘉怡，哦，嘉怡 you are not here also first 2 class not here I just came back。赵泽宇，一收四，陈少涵here as well。陈卓，李乐山，彭奕成，赵新成，forgive and forgive。Okay, all right. No. Okay, I need to label it。黄玉涵，何玉兴，陈玉兴。
这我们去的时候，今天没有，都是那个，我们这边是非常少，比较少。
Yeah，这是什么？哦，忘记这个 DSC 换其实这个 OK。
Go to toilet.
OK for you
PS4.
PS1 哦 PS1 OK OK PS1 3 OK 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 it's just Sing and yes Jasmine right Sing Jasmine Okay, in case I didn't take your attendance, right? So please come to me after class, and then I think our class still got spot. So if you or any one of you cannot sign in after third round, please immediately email me on Sunday night or Monday morning. Okay, so to get you into the this class, if there's any one of you wanted to join. Yeah, we should be able to accommodate you. Okay. So let's continue. A congruence of the form of AX, congruence V mod M, where X is an unknown integer, is called a linear congruence in one variable. Actually, this is secretly a linear Diophantine equation. Okay, linear Diophantine equation. Okay, did you realize this is secretly a linear Diophantine equation? Okay, it's because AX modulo B mod M. What does this mean? This means that AX minus B is divisible by M, or in other words, AX minus B is equals to a multiple of M. Okay, so if you rearrange this, what is this? AX minus KM. If I really want to make it similar as what you see before, how about make this K to be Y minus MY is equals to B. Okay, so it's a linear Diophantine equation actually. Okay, where you remove one of the term by introducing the mod. Correct or not? Okay, so you make it a zero mod M. Okay, so let's try this. Okay, so let's try this. Let's show you what I meant here. So solve the following linear congruence. Okay, so there are two of them. Let's solve the first one first. Okay, so meaning what x you put in,
such that you multiply to 4, you get 7 mod 9. Okay, you don't need to get exactly 7, but then you need to get the same remainder with 7. Okay. So let's try the first method. I'll show you the second method later. See which one you like. But let's solve it with what you know first. Linear differential equation. Okay, let's solve it using the method yesterday. So to solve 4x, solve 4x to 7 mod 9, it is equivalent to asking, it is equivalent to ask if there exists S and K in Z such that 4x minus 7 equals to 9. Okay. Or in other words, this is a differential equation of 4x minus 9k equals to 7. Okay, so checking your knowledge from linear from the very start of this class, right? I highlight for you. When does this equation have a solution? When the GCD of 4 and 9 divide 7. But GCD of 4 and 9 is what? 1. 1 divide 7. Okay. So if you have a solution, you will have infinitely many of them. Okay. So can you find just one first? Can you find one solution first? I mean, now the number is quite small, right? You should be able to do in an inspection. Yeah. X equals 2. X equals 4. And then minus 9 equals to, sorry, K equals to 1. Hey, wait. 4, 16, 16 minus 9. Okay, good. Yeah, good. Okay. So, so by inspection, we take X equals 4 equals 1, such that 4 times 4 minus 9 times 1 equals to 7. 16. Okay, good. Okay, so from previous chapter, what do you know? There are infinitely many of them, right? So how do you figure out the infinitely many solution? So the solutions are for any integer z, maybe use n better. X will be equals to 4 plus something, right? And then k will be equals to 1 plus something, right? Or minus. We have a alternating sign here. Okay. So what's the thing you need to put here? What's the multiple of it? B over GCD, is it? Okay, so B over GCD. So first one, the B is minus 9. For K, you need to use the A. So here is 4. So 1 is 4 minus 9 and 1 is 1 minus 4. Okay, but we only care about X, right? Okay, we only care about X. Okay, so in this case here, what are the X's you not need to know? So your solution is knowing up to mod 9, yeah? So hence, X is equals to 4 mod, sorry, 4 mod 9. So you can see that this part here is divisible by. Okay. You want to check this? Okay, so do the sanity check. Okay. Put 4 here. 4, 4, 16. 16 minus 7 is 9. Okay. Good. You want to try a different number?
let's say, what are 4 mod 9? What else are 4 mod 9? 13? 13, right? Correct? 13. So it's 13 times 4. What do you get? 52. Okay. Is it 52 equal to 7 mod 9? So 52 equals to something times 9. 5. 5 times 9 is 45. So 52 minus 45 is 7. Okay. Good. Good. Okay. Let me present you another method. Maybe this one will be easier. This method is brute force. Okay, so what do I mean by brute force here? Because how many possibility you can put in here for this x? This is mod 9, right? There's really only 9 number you need to check whether it's true or not. So you just compute all of them. Okay, so basically what you do, you list down all of them. So here I'll list x mod 9. And then what we care about is for x mod 9. Okay, see which one get you the 7. Okay, so 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, and then you multiply by 4. So 0, 4, 8, 12, 16, 20, 24, 28, 32. Like that. Okay, so then you reduce mod 9. Okay, everything you reduce mod 9, reduce mod 9, reduce mod 9, reduce mod 9. Okay, what you see is 3, 7, 2, 6, 1. Okay. 3, 7, 2, 6, 1, 5, 0. Oh, okay. I'll repeat that. Okay. So you can see that there's only one x mod 9 will get you 7. Make sense? Okay. Yeah. Since I present this to you already, right? I think this question, second question will become easier for x mod 10, mod 9. So this is equivalent to what? For x mod 1, mod 9. So you just go to this table and find where you get the 1. Where you get 7 mod 9. Okay. And you can also use the method 1 to practice to see what's really happening. Any question for now? For question? No? Okay. Yeah. Quite straightforward. These calculations seems very easy, but there are deep concept behind it. Okay, and then you can do this mod 6. So this one just left as exercise. Very straightforward. Okay, let's continue. Let's continue. So this is a new theorem here. This theorem is kind of a restatement of what we know last time. Okay, restatement of what we know last time. But then the second line is a bit special. Okay, so first line is if your GCD of A and M is D, then the linear congruence to have solution if only if D divide M. So this is very similar to what we had just now. Linear Diophantine equation. If your GCD divide B, and when D divides B, right, they are exactly what D solution mod M. Okay, so this is what we had just now. Why just now we only have one solution? Because our GCD is 1. So there's only one solution. Okay, so if you have more GCD, then you have equivalent numbers of solutions. Okay, is it understandable? Okay. Yeah. There's some proof. This proof is very interesting. It uses the we have introduced like cancellation law, all sort of that. So very interesting if you want to have a look. Okay, and then if A and M are relatively prime integers and B is integer, another integer, then AX equals B has exactly one solution for M. Yeah, this is what we talked about just now. If your GCD is 1, then this has only one solution. Okay. Yeah, only has one solution. Okay, so this is related to what I said just now. I removed the column that has that's not relatively prime to 6, right? Yeah. To make sure that there's only exactly one solution. This is what I did just now. Where's my table? Yeah. Here's my table. Oh, my table is here. Okay. So this is what I did just now. I removed these columns so that I have exactly one. Let's go on. Okay, then this will motivate this definition here. So let's say n and m, the GCD is 1. Then the solution to this congruence is what we call the inverse of A. Okay, so why is this the inverse of A? Because this x, when you multiply to A, you get 1. This is the inverse. Okay. So for example, in your usual number system, right? What's the inverse of 2? It is 1 over 2, because this is the number that you multiply to get 1. Okay? Yeah. And so in this world, if you have a integer A that's GCD with your mod m is 1, that multiply to A, you get 1. This is called the inverse. And from here, you can see that it is unique actually. This inverse is unique. Why? Because from the previous theorem, right, it tells you that how many solutions you can get for this linear congruence here. Only one. Okay, only one solution that fix this. Okay. Because the GCD is 1. And so there's exactly one solution. So it's unique. So to be an inverse, you have to be unique. Okay, so let's do some examples. So find the inverses of 1, 2, 3, 4, 5, 6, mod 7. So in this case, it means that you want to find what things multiply to 1, what things multiply to 2, what things multiply to 3, 4, 5, 6. You get 1. You get 1 mod 5. Sorry, mod 7. Okay, I give you try maybe 2 minutes. Very quick one. Quick exercise here to see when you get 1. Okay, let's try. So 1 times 1 is 1, right? Very straightforward. How about 2? What should you multiply with? 4? Can you try 4? Okay, so 4 times 2 is 8. So 8 is 1 mod 7. Good. How about 3? 5. Okay, so 3 times 5 is 14. So 14, sorry, 15. 15, so 15 is 1 mod 7 because minus 14 is 1. How about 4? 2. 2. Okay, 2 again because 2 times 4, 4 times 2 is the same. 5, I guess, is the same as well. So 3. How about 6? 6 a bit special. 6 itself. Okay. So it is itself inverse of itself. Good. You can find inverse for all these precisely because 7 is a prime. So any other number with this prime should be relatively prime. Any number is relatively prime to a prime number unless it is the prime number itself. Only 1 and the prime itself divide. Okay, so this is it for this part here. Let's see the next thing. Okay. Okay. Next, find the inverse of 13 modulo 31. I see if there's any special about this thing here. Okay, there's something. Okay, this part is not special, but we're gonna use this. So can you find this quickly? Can you find this quickly? This part is not important. The more important part is next part. Can you find this quickly? What's the inverse? So meaning 13 times what? You get 1 for 31. I think there's no trick to do this. Just by try and error, just try until it works. Maybe a bit painful, but one way you could try is start with multiple of 31. No? Okay, so maybe 31, 62, and 93, and then 1, 2, 4, and so on. But this is not the one you care, right? You want to know up to these plus 1, right? So 32, 30, 63, 94, something like that. Okay. See which one you can get by 13 multiplied by something. Maybe let's go a bit further. 1, 5, 5. And this one is 1, 5, 6. Okay, anyone got it? Got it? 12. Okay, a bit large. How do you find 12? You just try 0 up to 12. Unlike what I do. Okay. Yeah. So you try divide by 13, 13, 13, 13, 13. Hey, this one is divisible. Okay, good. Okay. It's 12. Okay. So 12 is an inverse. It's the actually because there's only one of it. Inverse of 13 mod 31. Okay, good. So remember 13 is mod 12 is the inverse of 13 mod 31. So now we're going to solve this congruence. Okay. So we're going to solve 13x congruence to 7 mod 31. So in this case here, you can do what we did just now, either linear differentiating equation or you want to list everything. But listing everything here, how many things you need to list? 31 of them. Okay, so instead of doing that, we will use what we know about congruence. So we're gonna replace this with an easier congruence. Okay. So how to replace this? So if you can replace any term inside the product, you can replace this congruence in the just now. Well, you know that since the GCD of 13 and 31 is 1, okay, we know the inverse. We know the inverse. We know the inverse of 13 mod 31 exists. And from the previous example, we found that it is actually 12. So what can we do? So Remember that we can just multiply 12 on both sides. Still remember, our congruence will preserve under multiplication. Okay, why is this nice? Because these will exactly return me x on one side. So we just need to compute what's on the other side. So other side is 84. So what is 84 mod 31? Huh? 20? 22. So x is. You can do some sanity check here. Do some checking. You can try check like 13 plus times 22, is it 7 mod 31 or not? You can do this check. What is 13 times 22? Kind of big. Okay, let's do it. So 6622. Okay, 6622, 282. Sorry, 2x6. Okay, and then 2x6, how is it divisible by 31? How? 4, 5, 6, 6, 7. Oh, 9. 9 is the largest one. 9, 2, 7. So 9 times 31 plus equal plus 7. Or in other words, 279 plus 7. Okay. Good. Okay. Yeah. Sure. How about this one? I'll let you try. Solve this linear congruence. Curve x equals to 66 mod 39. I'll let you try 3 minutes. Okay. Right. Anyone got answer? Anyone got answer?
Anyone got answer? Still calculating? I mean, I teach you at least 3 ways to solve these, right? You can use a linear dialectic equation, or you could use the brute force method, but then here got 0 to 39 to try. Or you could use the simplification. Okay, if you can simplify it. 除三. How do you divide by 3? Oh, wait. Let me see. What are you trying to do? Are you trying to use? Oh, so you are using. You're trying to use this theorem. You're just trying to use this theorem. Okay. Sure. If you want to use this, I think it works. Yeah. Yeah, you can use this. Let me think. If you use this, then your solution will exist in a smaller mode. Then you need to put it back. Yeah, you need to put it back. Yes. Yeah. Yeah, you can try that. You can try that. Sure. I can write that down for the next solution. What if we don't do that? We don't do double job. Similarly, you should observe that 12 and 39, that GCD is 1. Hey, wait. Am I wrong? Yeah. 12 and 39. 39 is, 12 and 39 is not GCD 1, right? 3. Yeah, thank you. Wait, is something wrong here? The GCD is not 1. Why can I find the inverse? Sorry? Divide 3 for all of them. Yeah, this is what your friend suggested. Let me think. Hey, the GCD is not 1, but then why the inverse exists? So let me try. So wait, I wrote something weird here. Let's see. What is 12 times? Let's check my stuff first. So 12 times 16, what do you get? 196, is it correct? Yeah, okay. So what's this mod 29? So let's check it. 29. It's 1 off. Yeah. Oh, this one, the GCD is not 1, but there is an inverse. It's possible. I think. Kind of possible, right? Okay, so this case, the GCD is not 1, but then it's invertible. Okay, so, well, so if we don't do the divide by 3 thing, so actually not that. 12 times 16 is 1 mod 39. Okay, then you just multiply 16. And then what do you get? You get x equals to 408. Wait, let me see. Okay, yeah. So maybe you can simplify 66, is it? Wait, why did I put 36 here? Am I crazy? A bit crazy, what I do here. Wait, let me see. Right, they are correct. Okay, I think my final answer is wrong. What's your final answer? 66 times
What's 66? Okay. Huh? 12. Is it just 12? Oh, x equals to 12. Okay, sure. X equals to 12? Wow, I wrote something weird, then my solution still correct. So weird one. Okay, let's continue this. 66 mod 39 is what? 27, like that. And then what is 16 times 27 is what? Ah,
说可以把16拆成28。
16拆成28 Is it easier? Is it easier? Yeah, let's try our magic. I got 10%. So 54 is easier, right? So 54 should get 15.
这里的一定
Sorry?
12 times
啊
16 is equal to
错了
192
192
啊。
Wait, let me see. Oh, that's my problem. So that's why I think this is weird. Okay. Okay, sure. That's why. Okay, that's why it's wrong. Okay. I think then in that case, really have to do your method. Yeah, that's why I feel weird, because GCD must be one the inverse only exists. Okay, good, very good. Okay, so let's try the theorem. Oh, let's go. I think there's no only way again. Okay, so let's bring this. Okay, so let's use this. Well, yeah. So good. Okay, so 12x mod 66, 39. Okay, then this would imply that. Okay, so you basically pull the tree out. And this will imply that 4x equals to 22 mod 13. And then this will imply that 4x is equivalent to 9 mod 13. 9 mod. Okay.
In fact, I think according to the law becomes 2x minus 11 for the law 13.
2x congruence to 11 mod 13.
Yeah, I could according to the theorem.
How?
帮我们电脑。Because we see the C, the number C, from the 2 times 3.
Oh, you mean take even more stuff out?
Yeah.
Okay, sure. So, okay, sure. Okay, so either you can go this way or you go the next way. You can go, instead of taking, can we take 6? Oh, I think you can. So let's try. So you can go the other way. So this is one way. Second way, there's a lot of ways I should see that they should get the same answer. So 2 times 6x equals to 2 times 11 times 6 mod 39. And then we see that the GCD of 6 and 39 is 3. So then you can remove the 6 such that you get 2x equals to 11 mod again 13. Okay, so let's pick one to continue and then you can try the other one. So let's pick this. Then 4 and 3, the GCD is 1, right? Okay, now in this case, we should be able to find the inverse. So what's the inverse? So the inverse here is 4, 3, 12, 4, 4, 8, 10. 10. Okay, good. So 4 times 10, so good. So then we multiply 10 to both sides. Okay, so x will be equals to what? 90 mod 13 is what?
12.
12. 12. Okay, John, are you interested calculating the other side? The other side, you get 12 as well, right? 12 is the inverse. Wait. Or I guess 20. 20 is too much, right? Can we get the next one? 20, if 20 work, then 7 will work. Okay, 7 will work. 7x 13. Then you get x equals to 77 mod 13. So what is 77 mod 13?
It's the same 12.
Same. The same. 12 also. Okay, 12 mod 13. Okay, so since it is 12 mod 13, right? So what does this mean? Huh? Yeah. So how?
就3个键。
Yeah. So because your solution is 12 mod 13, but your original solution is in 19, right? Okay, so then x equals to 12, and then add by 13, what do you get? 25, 38, mod 39 will work. Okay, so this also answered this question, right? This theorem question. Okay, so if your GCD of A and M equals to 3 in our case, there's exactly 3 solutions. Okay, yeah, D solution. Our D is 3. Okay, or not? Yeah. So the GCD of 12 and 39 is 3. Not that. The GCD of 12 and 39 is 3. Okay, so by previous theorems, they are exactly 3 solution. Mod 39. Okay, so if you have these 3 solution mod 39, you mod by 13, you reduce. Okay. What time is it? Okay, almost finished. So before we end, I want to mention about this Chinese remainder theorem. Okay, so next part we will learn the Chinese remainder theorem. So basically, why is this Chinese? Because there's all kinds of people they want to calculate their troops. Okay, so they try to group them into groups. Okay, uniform groups, and then from this grouping, right, they can kind of figure out what's the total number. Okay, so this is the power of this Chinese remainder theorem. Okay, so basically, you solve a system of congruence. Okay, in linear algebra, you solve a system of linear equation. So in number theory, we solve a system of congruence. Okay, once you know this number will satisfy some linear congruence, the same number, yeah, same number satisfying this system of linear congruence, then you can find what this solution is. And this solution is unique. Okay, unique up to some modulo some number. Okay, so meaning you know it is equivalent up to knowing their remainder. Remainder with this number here. So what's this number? This number is very interesting. you just multiply all this modulo together. Okay, this modulo could be very large. Okay, just to remind you, could be very large. And then the funny thing or the interesting thing is this solution is unique up to modulo. Okay. Okay, if no question, please enroll by this Sunday. If not, message me, and then assignment due next Wednesday. If you need hints, you can try and ask from me. I'll tell you in class. Okay, if no problem, happy weekend. See you next week.